Hello students. Today we will discuss about current electricity. See, actually what is current electricity? Current means the flow or movement. Electricity means flow of charge. See, the charge movement is called electricity. Here, the current electricity tells something about the moving charges. The moving charges produce a current of electric charges. So, here in this lesson, we need to know some of the terminology of the moving charges, and thereby we also learn something about Ohm's law. Okay. See, first of all, in this current electricity, the electric strength is defined by the rate of flow of charge through a conductor per unit cross section is called strength of the electric current, that is represented by here I is equal to Q by T. So strength of electric current. Okay. So in this way, if the instantaneous current, that means the electric current per unit time is can be written as, that means I is equal to limit delta t tends to 0, okay, dq by delta q by delta t. Okay, this is the instantaneous current at a particular time, that means the flow of charge. Delta q represents the change of flow of charge, delta t represents the change in time, and this can be written as dq by dt. Okay, so the change in current by change in time. So here I is equal to charge per unit time, and the instantaneous current is defined like this. So what is the unit of current? Unit of current is ampere. Ampere. Okay. See, what is the definition of ampere? Ampere is coulomb, 1 coulomb per 1 second. If 1 coulomb of charge is flowing through a conductor of unit cross section in 1 second, that means flow of 1 coulomb of charge in 1 second is called 1 ampere. So the unit of electric current is ampere. Okay, so this is the basic definitions of electric current, and we see some of the applications of electric current now. What are the applications of electric current? Okay, applications. Here, if a charge is flowing through a conductor of cross section, see here, if the charge is flowing in between a time limit of t1 and t2, okay, then we can write here dq is equal to between the limits t1 to t2 I dt, because we know that, since we know that I is equal to dq by dt. This is the average current that flows in between a time of t1 and t2 seconds. Okay, so in this way the average current is represented by this integration form. And if there are a number of charge carriers, that means number of charges is represented with n, then in this case what will be the average current? Okay, I is equal to nq by t. N is the number of charge carriers or number of electrons that are carrying the charge per unit time. This is the average current in case of number of charged carriers. Okay. So, in the next example, if a charge is moving in a circular loop, okay, a charge is revolving in a circular loop with a velocity v, suppose with a velocity v, and the radius of the circle is r. Okay, so a charged particle is moving in a circular path. So here, what could be the time period of the revolution of that charge? The time period will be 2 pi r by v. V is the linear velocity. Okay. So this is the time period of the charged particle. So what is the electric current in case it is produced by the revolving charged particle? Electric current is, we know that, q by t. That means here the time, that means the time period of one revolution can be written as this one, q by this value. So this can be written as, what is the inverse of time period? Frequency. We can write it as frequency. Okay. So actually, what is frequency? Omega by 2 pi in the circular motion. If omega is the angular velocity, what is the frequency? Omega by 2 pi into q. It can be written as q. Okay. So this is the relation between electric current when a charged particle is moving in a circular path. Okay. So in this way we can understand what is exactly electric current, that means the flow of charges. Next we move to the definition of electric density. Okay. Electric density. See, what is the density of electric current? What is the density of electric current? It is represented with J. See, electric current density is a vector having a magnitude of an electric current passing through a conductor. Okay. The formula we can be used with this electric current density is, it is an instantaneous density, and we can write it as limit delta s tends to 0, delta I by delta s. Okay. So through a unit cross section of area, the passage of electric current signifies the electric density. In this way we can write it as di by ds. Okay. So here, if the surface area is parallel to the electric flow of current, okay, then the equation will become, you can write it as I by S. Okay. So here, if we take this equation, that di is equal to j ds. Okay. So in this way, if the normal to the surface area through which the electric current is flowing is making an angle theta with the surface area, then how this equation will become is, that means the normal drawn to the surface area through which the electric current is moving is making an angle theta with the electric current. Then in this case it can be written as di by ds cos theta. Ds cos theta is a component which is in the direction of electric current. So here, if you take in this form for this equation, and if we integrate after taking this ds cos theta, okay, so j dot ds cos theta, this is in the form of scalar product. So I is equal to j bar dot ds bar, okay, the dot product of electric current density and the small surface area. Then we need to integrate to get the total electric current passing through the entire surface area. After integration we will get the total electric current, okay. So the density of electric current is represented with J and the units are ampere per meter square. This is the unit for electric current density, okay. So in this way we can get the electric density for different surfaces based on the surface area of the flow of charge, okay. Next we see what is drift velocity. Drift velocity of electric current. What is drift velocity? It is represented with vd. D means drift, okay. So the drift velocity is the average velocity acquired by the charged particles when it is conductor is placed in an electric field. When the conductor is placed in an electric field, see, the charge carriers will be moving in the direction of, so opposite to the direction of the electric field. That means they gain some velocity to move through opposite to the direction of electric field. Why opposite to the direction of electric field means, generally the charge carriers are electrons and the electric field is from positive to negative direction. So the charge carriers will move opposite to the electric field. This is electric field and the velocity Vd will be in the opposite to the electric field direction. Here the drift velocity is the average velocity acquired by the charged particles when the conductor is put in the electric field. So how to represent drift velocity means electric density by Ne, where N is number of charge carriers per unit volume. See, E is charge of electron, J is current density, okay. So here the drift velocity of the electron is around 10 to the power of minus 4 meters per second, and I've already told you that drift velocity will be opposite to the field direction, okay. Drift velocity is proportional to the electric field applied. So if the field is increased, drift velocity will also increase, okay. So this is about drift velocity, and we will see one more term in this definition part, that is mobility. Mobility of what? Mobility of charge carriers. So mobility of charge carrier depends on what? See, the mobility is defined as the drift velocity acquired by the charged particles per unit electric field applied. That means the mobility represented with mu. Mu is equal to Vd, the magnitude of drift velocity by electric field. So this means when the electric field is applied and the charge carriers have got some drift velocity acquired, some drift velocity, the how much the field is applied and how much the drift velocity has acquired by the charged particles will represent the mobility. Mobility is the angle of freedom to move is called mobility. So mobility depends on the temperature of the material and the nature of the material and the electric field applied. So these are the some of the definitions we need to learn in current electricity before going to the some laws and problems in this chapter. Okay. Now we see what is Ohm's law. What is Ohm's law? See, Ohm's law says that the electric current strength depends on the potential difference applied between the two ends of the conductor. Okay. So that means the strength of electric current flowing through the conductor is directly proportional to the potential difference applied between the ends of the conductor. That means if the potential difference is applied is more, the flow of charge, that is the electric current, will be more. So that we can write in this form also. We equate this equation by taking in the denominator the resistance of the conductor. Okay. So I finally has become in this form. So proportional to V, and the resistance part will also take part in this equation, because if the resistance is of the conductor is more, the electric current will be less, because the resistance opposes the electric current. So this equation can be written as V is equal to IR. Actually, the Ohm's law is not a basic law or not a derived law. This is only an empirical equation. An empirical equation means it is only based on observations and experiments. This Ohm's law doesn't have any theoretical support. Okay. So if you observe this Ohm's law in a microscopic way, little bit closely, so we can write in another form like NEVD, drift velocity into electron charge and number of charge carriers. Okay. So we can write it in the form of NEVD. See, the sigma is the electrical conductivity of the material or conductor. Okay. So here, what is the electrical conductivity is more, the electric current will be more. At the same time, the density is also more. Okay. So this electric current and the electric density or the relative terms almost same, have the same meaning. And see, if there are some metals which obey the Ohm's law, then they are called ohmic conductors. Metals or some materials, anything that obeys Ohm's law will come under the category of ohmic conductors. And if any other materials would doesn't obey the Ohm's law are called non-ohmic conductors. That example, electronic valves, thermistor, gases, crystalline filters, these are all called non-ohmic conductors. Okay. So the velocity and electric current graph, the potential difference and the current graph in Ohm's law can be represented with this graph in this way. Okay, a straight line passing through in between the I and V, electric current and voltage on potential difference on y-axis, electric current on x-axis. Okay, if this theta is the angle made by the graph with this electric current, then the tan theta, the slope of the graph, can be written as V by I. Okay, the slope gives opposite side by adjacent side. That means potential difference by electric current. So this gives the slope. So here, in this way, we can go to the next classes with the help of these definitions. Okay, in next class we will see some more topics in current electricity. Okay.